Hello and welcome back. Today we'll talk about oil recovery methods. We know that oil moves through the reservoir towards the production wells thanks to the pressure difference. It flows on condition that pressure in the reservoir is higher than at the bottom hole. Then we start developing a field. Reservoir pressure is often high enough to ensure oil inflow to the well. With time, reservoir pressure changes gradually and we need to maintain it. To do so, we can inject water or gas. We will have a special video on it. Depending on the means by which production is achieved and the source of reservoir energy, we speak of three recovery methods: primary recovery, secondary recovery, tertiary recovery. In a standard case, when we deal with a conventional oil field, we move from primary recovery at development stage 1 to secondary recovery at stages 2 and 3, and on to tertiary recovery at stages 3 and 4. And conventional fields of heavy, ultra-heavy or very viscous oil require a special approach, so we usually get to tertiary recovery straight away. However, let's not run ahead and start with primary recovery. Primary recovery is natural production achieved thanks to internal energy of the reservoir. In petroleum play, there are many forces that influence fluid movement. Some of them are natural and some are caused by man, but the total of these forces and conditions is called oil or gas reservoir drive method. There are 5 oil reservoir drive methods: solution gas drive, gas cap drive, compaction drive, gravity drive, water drive. The first 4 drive methods are also known as depletion drive methods. In real life, a single drive method occurring in a reservoir is a very rare case. More often, we deal with a combination drive combined either in time, one drive method follows another, or in space, different drive methods active in different areas of the fields. We will start with depletion drive methods where the reservoir is isolated and has no external support source such as active aquifer, a water bioformation, so it has to use its own energy to produce oil. It may be a field where oil is contained in isolated sand lenses, or a field that had fallen under structural changes such as faults. In such reservoirs, energy comes from fluid expansion or rock compaction. Then energy comes from expansion of gas that is dissolved in oil. We call it solution gas drive. Gas has a high compressibility, so as it comes out of solution, reservoir pressure drops not so fast. This drive method is typical for slightly deepened reservoirs with low reservoir properties and viscous oils. As we produce oil from the reservoir, its pressure falls below the critical point and gas starts coming out of solution. Typical development history of such a reservoir looks like that. Reservoir pressure keeps on falling for the whole development period. Thus, the difference between critical pressure and current reservoir pressure gets bigger and bigger. Production gas-oil ratio remains constant for a while. Then so much gas comes out of solution that gas permeability increases, and production gas-oil ratio may become several times higher than reservoir gas-oil ratio. It happens because well-produced gas that comes out of both produced oil and oil that is still in the reservoir. As reservoir oil loses gas, it becomes more viscous. Further on, production gas-oil ratio drops as we start producing oil with almost no gas in it. Oil production starts declining immediately after reaching its peak value. Oil water cut is very low. Ultimate oil recovery, depending on reservoir properties and oil viscosity, varies from 10 to 40%. Another depletion drive method is gas cap drive. It also uses gas compressibility as a source of energy. But how is it different from solution gas drive? In this case, we already have some free gas in a reservoir, which makes up a gas cap at the top. This gas cap is evidence of reservoir pressure being close to saturation pressure. So as we start producing oil, very soon reservoir pressure will drop below critical point and gas will start coming out of solution, contributing to the cap. Thus, we have 2 sources of energy: gas cap expansion and solution gas expansion. As we develop such a field, reservoir pressure keeps on dropping. How fast this happens? depends on oil production rate and initial volumes of oil and free gas in the reservoir. As gas cap grows and gas-oil contact moves down, at a certain moment, wells start producing gas from the cap, so production gas-oil ratio increases and oil production rate decreases. Oil produced is free of water. Ultimate oil recovery of such a field is up to 40 to 60%. Compaction drive is another depletion drive method. It manifests itself as inner pore pressure drops down, so the resulting mechanical pressure of the rock increases, which causes it to crumble and compact. Sometimes Earth's surface itself can subside due to this compaction. This reservoir drive method can be observed in loose sandstones and limestones. A very dramatic compactions took place on aquifers fields in the North Sea, where the sea floor unexpectedly subsided by almost 6 meters, and special equipment was required to jack up several sea platforms at once. Gravity drive uses oil heaviness as a driving force. It happens that the plate is completely isolated from water, and there is no gas, free or dissolved. Such a situation is rather rare. It usually occurs at a late development stage in a reservoir what was previously driven by solution gas. This drive method can be efficient in steeply dipping reservoirs. Oil production rate is very low, and recovery factor is 10 to 20%. Gravity force in a reservoir acts very slow, but in the long run can result in good oil recovery. Combined with the recovery factor observed at the preceding stage of solution gas drive, the ultimate recovery may be as high as 50%. Water drive uses water as the force pushing oil towards the bottom hole. It may be edged water coming from the sides of the deposit or bottom water coming from the water-bearing formation below the oil reservoir. As we produce oil, water takes its place, so the oil-water contact is rising. This usually occurs in lithologically homogeneous and highly permeable reservoirs close to water. Water drive is the most efficient among the 5 natural drive methods we have learned. Water, especially formation water which is salt, is very good at displacing oil from the pores. Both this fact and favorable geology that usually accompany water drive method result in high ultimate recovery factors, which may be as high as 65 to 80%. Once again, in most cases we observe combination drive, when one drive method replaces another or different drive methods are active in different parts of the field. What development strategies are used in primary recovery cases? If we deal with solution gas drive and we expect oil-water contact to be more or less static, we use regular uniform four-spot or free-spot well pattern. If we expect oil-water and oil-gas contact to move, we design our well pattern trying to account for this movement. I need to say that pure primary recovery is a very rare case today. It happens on depleted fields that were in production since 1915s, that is, before people started to use water flooding on relatively small shallow fields with active edge water and viscous oil, or on low permeability shallow reservoirs. We know from experience that primary recovery leaves much oil in the reservoir, so we typically start using secondary and tertiary recovery methods as used as we can, trying to maintain reservoir energy. What are these methods? You will see in our next video. See you!